Greetings for the day, dear students. Today I am going to start a new topic, that is bioenergetics. I have divided this topic in two parts. Today I will discuss part 1, that will cover bioenergetics and laws of thermodynamics. What is bioenergetics? It is the quantitative study of energy transduction, that is release, storage and use of energy in living cells, along with the study of the nature and functions of chemical processes underlying these energy changes. Now we will take the laws of thermodynamics. Number 1. For any physical or chemical change, the total amount of energy in the universe remains constant. Energy may be changed from or it may be transported from one region to another, but it cannot be created or destroyed. Second, the universe always tends towards increasing disorder. That is, in all natural processes, the entropy of the universe increases. The total disorder of a system must increase if a process to occur spontaneously and called the entropy. The reacting system may be an organism, a cell, or two reacting compounds. The reacting system and its surroundings together constitute the universe. In laboratory, some chemical or physical processes can be carried out in closed systems and no material or energy is exchanged with the surroundings. However, living organisms are open systems. They exchange both material and energy with their surroundings. Living systems are never at equilibrium with their surroundings. Now we see some terms. The most important one is Gibbs free energy. It is represented by the symbol capital G. G expresses the amount of energy capable of doing work during a reaction at constant temperature and pressure. When a reaction proceeds with the release of free energy, that is, when the system changes so as to possess less free energy, delta G has a negative value and the reaction is said to be exergonic. In endergonic reactions, the system gains free energy and delta G is positive. The unit of delta G is joules per mole or calories per mole. Next term is enthalpy. It is represented by the capital letter H. H is the heat content of the reacting system. H reflects the number and kinds of chemical bonds in the reactants and products. When the chemical reaction releases heat, it is said to be exothermic. The heat content of the product is less than that of reactants and delta H has a negative value. Reacting systems that take up heat from their surroundings are endothermic and have positive values of delta H. The unit of delta H is joules per mole or calories per mole. Next term is entropy. It is represented by the capital letter S. S is the quantitative expression for the randomness or a disorder in a system. The unit of delta S is joules per mole or Kelvin. Under the constant temperature and pressure changes in free energy, enthalpy and entropy in the biological systems are related to each other by the equation delta G is equal to delta H minus T delta S. Here delta G is change in Gibbs free energy of the reacting system, that is, it is G of products minus G reactants. Delta H is equal to change in enthalpy of the reacting system, that is enthalpy of products minus enthalpy of reactants. Here T is absolute temperature and delta S is equal to change in entropy of the reacting system, that is entropy of products minus entropy of reactants. Living organisms preserve their internal order by taking free energy from their surroundings in the form of nutrients or sunlight and returning to their surroundings an equal amount of energy as heat and entropy. Here we will understand this by taking an example, which is oxidation of glucose. Aerobic organisms extract free energy from glucose obtained from their surroundings by oxidizing the glucose with oxygen, also obtained from the surroundings. The end product of this oxidation reactions are carbon dioxide and water, and they are returned to the surroundings. At the end of this process, the surroundings undergo an increase in entropy, whereas the organism itself remains in a steady state and no change occurs in its internal order. This we can understand with the help of this simple diagram. Here the chemical reaction shows that is glucose is oxidized to give carbon dioxide and water. The reaction is C6H12O6 plus 6O2 gives rise 6CO2 plus 6H2O, and this can be diagrammatically represented as that on the reactant side there are 7 molecules. The pink dots represent oxygen and there are 5 molecules. 5 such pink dots are there which represent, 6 such dots are there which represent 6 oxygen molecules, and the black square represents the 1 molecule of glucose. Here oxygen is a gas and glucose is a solid. When these 7 molecules react, they give rise 12 molecules. That is, the green triangles represent carbon dioxide which is in gaseous state, and the flower form, blue colored flowers or the cross represent water molecules which is a liquid. Here we can say 6 green triangles which represent 6 molecules of carbon dioxide and 6 crosses which represent 6 molecules of water. Whenever a chemical reaction results in an increase in the number of molecules, as we have seen in the case of oxidation of glucose, initially on the reactant side there were 7 molecules, whereas on the product side there are 12 molecules. So whenever a chemical reaction results in an increase in the number of molecules, the entropy of the surroundings increases. Whenever a solid substance is converted into liquid state or gaseous state, it forms the entropy of the surroundings increases, because this transformation allows the molecules more freedom for movement. So we can say that the entropy of the surroundings is increasing. So this was all about the bioenergetics part 1. In the second part, I will tell you some more terms and more informations about the bioenergetics or the laws of thermodynamics.